Today we're going to talk about the automation tools that are transforming the way we do synthetic biology. As of 2013, most of synthetic biology still involves the sorts of manual procedures that you have learned in this course. You make DNAs in small sets, giving tender loving care to each construct, and you run manually poured gels and you store things in an ad hoc manner in the freezer. There's a great deal of effort underway to change the way we do genetic engineering to make it much easier and quicker to perform. The use of liquid handling robotics is already extensive in the larger biotech companies and government labs, and these instruments are being incorporated into the academic wet lab as well. This is accompanied by suites of software tools that manage the wet lab experiments, allowing them to scale, but much of the design process is also being automated in the form of design and verification tools. There are many good reasons to automate a wet lab experiment. When you perform complex manual tasks as an individual, there are issues with reproducibility caused by subtle differences in how each user conducts the experiment. When a machine does the experiment, it comes out more similar run to run, and more importantly, the run to run variability can be measured and this uncertainty factored into the experimental design. Automation and multiplexing also enable the miniaturization of experiments. When you do everything with a pipette in Eppendorf's, you use a large amount of reagent. When a robot does it, the reactions can be reduced to tiny volumes, even as small as 1 nanoliter, thereby saving space and reagent costs. Where automation is most useful is in increasing throughput. You all would probably have no problem doing 10 cloning experiments in parallel, but what if I gave you 100 or 1,000 to do? It is in the scaling of what you normally do in the lab to much higher volume that you encounter the need for robotics and automation. Though automation often requires high capital investments, the robots are expensive, and high consumable costs, the robot tips and barcode tubes cost much more than the universal tips and Eppendorfs that you use in the normal wet lab. There's often a labor savings cost associated with automation. Most of the price reductions in gene synthesis over the past 10 years have been the result of incorporating automation into the DNA fabrication pipelines at companies. Most usefully, automation enables higher levels of abstraction. Today, if I ask you to design a cloning experiment for a part, you will follow the source of thought processes that you learned in your tutorials, and you will expend a large amount of time and energy into making that one thing. If you instead use automated scripts for the design and robots to do the fabrication, you only need to provide a specification for the part and the rest happens automatically. So you spend less time dealing with issues of fabrication and low-level design and can instead focus on the more interesting aspects of the experiment. Automation has become fully integrated into most other fields of engineering and even in the biological space of drug discovery. The sorts of tools are generally referred to as CAD, which stands for Computer Aided Design, or CAM, Computer Aided Manufacturing. Both CAD and CAM now have counterparts in genetic engineering. CAM has been demonstrated with the Gibson, Golden Gate, BioBrick, and PCA fabrication chemistries, to name just a few. Though much of our fabrication is still done by hand, the only reason for this is that fabrication as a service has only thus far been provided for total gene synthesis. Efforts are underway to develop services for the assembly methods as a service, and these should be existent by around 2015. What this means is that the painful part of wet lab synthetic biology is disappearing, and software tools are playing a more prominent role in the day-to-day implementation of projects.